So, yesterday we looked at using the velocity difference between 2 points on a rigid body to analyze the velocities in a 4 bar linkage. So, you saw that if there are 2 points on a rigid body that are described by a vector r b relative to a, then the velocity of b with respect to a, if omega is counterclockwise, then this will be velocity of b relative to a, otherwise it will be, if omega is like this, then this will be the velocity of b relative to a. Okay. So, this is how the direction, or from the direction of the velocity you can determine the direction of omega. So, for planar problems omega will be positive counterclockwise, it is typically taken positive counterclockwise and negative clockwise. Okay. So, we also looked at the slider crank mechanism. So, we looked at 2 points on the same rigid body. In some cases, for the graphical analysis, we will have to consider points that are momentarily coincident, but on different bodies. So, take for instance an inverted slider crank like this. Okay. So, you have a block which is sliding. So, you have link 1, two, 3 is the block which is pivoting with 2, and then I have link 4. So, this is O4, this is O2, and let us call this point A. Okay. Now, at a particular instant, okay, so here I know the velocity of A on body 2. So, say this is my, let us just say I take it this way just for a change. Okay. So, let us say I take omega 2 as clockwise. So, I know the velocity. So, here if I actually look at A, I can say there is an A on body 2, there is an A on body 3, right, the pin, and I can also find a momentarily coincident point A on body 4. Okay. So, that is what we are going to consider. So, I am going to consider coincident points on body 3 and body 4. Body 2 and body 3, it's permanently together. So, they are always going to be coincident. So, the velocity of A on body 2 will be equal to the velocity of A on body 3. Okay. So, if I draw my, and if omega 2 is this and I am given R2, so I can say that it will be, draw my velocity diagram. Okay, it will be an absolute velocity because it is rotating about a fixed pivot, and this will be point A on body 2, which is also the same as A on body 3. Okay, because those two are. Now, if I look at the motion, so I want to relate, if I sit on 4, okay, if I sit on link 4, this point A3 is going to move along the link. Okay. So, I can write So, I know the direction of this. Remember, we have to know something about the other point that we take in order to relate two velocities, right. So, I need to know something. In the case of the 4 bar, I picked B, which was coincident with a body that was rotating about a fixed pivot, so that I would know the direction of that velocity. Here I know the direction of this relative velocity. So, I can relate these two velocities as velocity of A on body 3 is the absolute velocity of A on body 4 plus this relative velocity. Okay. So, in this I know completely the velocity of A on body 3, velocity of A on body 4. So, body 4, its absolute movement is pivoting about O4. Okay. So, if I take a point that is fixed to body 4, okay, I know the direction of that velocity. I do not know the magnitude because I do not know omega 4. Okay. And in the case of this velocity, how the two are slipping with respect to each other, the block and the path, I know the direction, but I do not know the magnitude of that slip velocity. Okay, that velocity is called the slip velocity. So, I use this to solve the velocity polygon, and I get, so I have, this is velocity of A on 3, then I have velocity of A on body 4 would be perpendicular to this, right, it would be perpendicular to this. So, and it is an absolute velocity. So, I again start from O, so this is perpendicular to O4 A on body 4, and then this, the slip velocity I know is along the direction of this. So, it is along this. So, I do not know which direction. So, but I know that it is, and it is also perpendicular to this one. So, this is along O4 A4. So, this intersection here gives me the velocity, the point A on body 4. So, now I have this velocity of A on body 3, my equation is equals this plus this. Okay. So, my slip velocity, so 3 is moving in this direction from A4. A on body 3 is moving this direction from A on body 4, which as you can see because of the clockwise rotation of the crank makes sense. So, it is moving away from that coincident point in this direction. Okay. So, this is how you do the graphical velocity analysis when you have, and this velocity will become important when we do the acceleration analysis, because when you have a sliding joint on a rotating path. Okay. Earlier when we looked at the slider crank, the path remains fixed. Okay. But when you are looking at inverted slider cranks, you are looking at a path which is also rotating, and in those cases the Coriolis acceleration will come into play, and that Coriolis acceleration is directly related to the slip velocity that you find from the velocity diagram. Okay. So, this is the case of the inverted slider crank. Now, we will look at the velocity image theorem, which is for So, So, when you are doing graphical analysis of mechanisms other than a 4 bar. So, for instance, if you have a mechanism like this, a 6 bar where another diode is driven by a coupler point of the, okay, in this case it is a slider crank, but you could, I could technically have a 4 bar also. I can just, instead of putting a slider here, I can just put a 4 bar and then, so it is basically a 6 bar. Okay. So, in mechanisms like this, once you analyze, so you have multiple loops in the mechanism. So, this part of it is essentially a slider crank, right. So, if I have O2, A, B, C, D and let's say 1, 2, 3, 4, 5, 6. So, this is O6. Okay. So, I can do the velocity analysis for O2AB, which is simply a slider crank. So, say this is my input link. Okay. Then the output that I am interested in is omega 6. Say that is the output that I am interested in, because otherwise there is really no reason. If the only output I was interested in is, so if 4 is the output, then I do not really need the rest of this mechanism, right. So, because the motion of this part is going to be independent of this. It is this coupler point C which is driving this diode, and I am interested in say omega 6 as the output of this particular mechanism configuration. So, an easy way. So, once I do the analysis of this 4 bar or 4 bar equivalent, the slider crank, I can easily find the velocity of this point C. So, essentially I have to apply the relative velocity equation sequentially in order to compute omega 6, right. So, I have to, so I keep writing. So, just as I do velocity of B equals velocity of A plus velocity of B relative to A, then once I find, so I do that to find omega 3 and the velocity of B, the magnitude of the velocity of B. Then after that, once I find omega 3, I will find velocity of C, then I will find velocity of D equals velocity of C plus velocity of D relative to C, okay, because each time I have to go sequentially. I have to keep looking for 2 points which are on the same link to do this, and then once I do this, I can now solve for, with this equation I can solve for omega 5 and omega 6. When I relate D and C, right, then I can solve for omega 5 and omega 6, because once I find omega 3, I can find the velocity of point C. So, let me just do that. Okay. So, once I find omega 3, right, I know the velocity of A. So, velocity of C will just be the velocity of A plus the relative velocity C with respect to A, which I can find out once I know omega 3. Then I relate C and D, and once I relate C and D, that is it, I can solve for omega 5 and omega 6. So, I know all the angular velocities in this mechanism. and with velocity, if I know the velocity of any one point on each link, then I know the absolute velocities of any point on the linkage. The velocity image theorem will help you find the velocities of say point C. We saw that yesterday when, so if I just do the velocity analysis of this, I have O, I have velocity of A, okay, which is perpendicular to O to A, and then I know the absolute velocity of B is along this path. I know B relative to A from here is along this path. So, this is perpendicular to AB, this is parallel to path of B. So, this gives me B. Okay. So, from here I have, from this equation I have velocity of B equals this velocity of B equals velocity of A plus B relative to A. Okay. From here I know omega 3, right. Omega 3 is AB by the length AB. So, if you look at this triangle, okay, then now if I want to find the velocity of C, I have velocity of C is velocity of A plus velocity of C relative to A. Okay. Now, when I do that, I already have velocity of A, okay, and velocity of C relative to A is going to be along that, right. So, I would have this. So, this also I know the magnitude now, once I know omega 3. So, I would just construct that vector like this, okay, to give me point C. Yeah. So, that then gives me the absolute velocity of C. The blue one is the absolute velocity of point C, okay, which I need for the next step, for this step, because then this becomes the input which is completely known. This one magnitude is not known, direction is known, again this one magnitude is not known, direction is known. So, again I can solve for omega 5, omega 6, but VC is what I need for that. Now, if you look at, so first what did we, omega 3, let us just determine omega 3 is from the velocity diagram, it is this length AB by AB, okay, and what would be the direction from this diagram? So, it is B, what would be the direction? B relative to A, and it is in this direction, which means omega 3 is clockwise, okay, omega 3 is clockwise. Now, look at the triangle small ABC in the velocity diagram. I have A, okay. So, I found omega 3 is clockwise, and if you look at each of the sides of this triangle, AB is proportional to capital AB, AC is proportional to capital AC, and BC is proportional to capital BC, because the whole thing is scaled by what number? Omega 3. it's scaled by omega 3. This one, I am just taking this outside. Okay. So, all the relative velocities on that body are scaled by omega 3, which means this triangle in the velocity diagram is similar to the original triangle ABC, and it is rotated how? And it is rotated 90 degrees in the direction of omega 3 in this case, because all these points belong to link 3. Okay. So, I do not really need to, so once and I could have other points on this that I am interested in, and all I have to do is construct in the velocity diagram directly instead of having to compute each of these velocities in this manner. If I construct something similar to the shape of that particular link rotated by that 90 degrees, then I can directly read off the velocities of those points. That is what the, so the velocity diagram is an image of the position diagram of the linkage, okay, with all the relative velocities scaled by omega of the link and rotated by 90 degrees in the direction of omega 3. So, you can see here, see the order A. So, this is, if you take this and rotate it by 90, this is what you would get, and scale it. You can see C has moved down. Okay. So, you should be careful when you construct in the velocity diagram, because if you put C on the other side, then that would be wrong, because that would mean that it has rotated counterclockwise. So, that is important, the direction in which omega acts. So, once you find omega for that link, then you can construct the image for the velocities. So, let me just write a couple of things. So, triangle ABC in the velocity diagram this applies not just to triangles, because any shape you can, any polygon for instance, you can break it up into triangles. So, it applies to any shape of the body. So, the shape in the velocity diagram would be proportional to and rotated by 90 degrees in the direction of omega. Okay. So, this is the so once you solve the first one here, you can directly then solve the second equation without actually, you can construct the image of ABC on the velocity diagram and then use that to solve for the next two velocities. Okay. So, that is the, That is the velocity image theorem. Now, what is another method for finding velocities that you have seen? Other graphical method, another graphical method. See, with the velocity difference method, I have to go through the whole, I can't jump to finding omega 6 just by knowing omega 2. I have to go through each of the motion transfer points, so to speak, to connect them and find all the intervening angular velocities before I get to the angular velocity that I am really interested in. Okay. So, I can't skip finding any of the intermediate angular velocities here, okay. But I may just be interested in omega 2 and omega 6, for instance. Okay. So, in that case we can use the method of instant centers. Okay. So, the method of instant centers, so the instant center is, what is the definition of the instant center? It is a point okay, that is one definition. So, relative to one, the point velocity is 0 with respect, it's only in some cases.
Relative to the instant center, the two links which have been considered act like rigid bodies.
The links are rigid bodies anyway. So,
I know, even together, even if they are disconnected links.
yeah, relative to the,
If I pick
see what you said initially was correct, you know, at that point the relative velocity is 0, which means you can imagine that one body is rotating in pure rotation about the other body at that particular instant. But for the purposes of velocity analysis, what is the basic definition of the instant center of velocity? It is a point common to both bodies. Okay. What else? There could be many points common to both bodies. What is special about this point?
The point, the relative motion of one body with respect to the other is pure rotation.
Okay, which means what? So, that point acts like a hinge, which means in this big scheme of things, what is happening to, what is the velocity of that point in both the bodies? So, it is a point common to two bodies, okay, whose velocity is the same. At that particular instant. Okay. So, let's start off with the our friend the 4 bar. And look at, so if you have, how many instant centers will you have when you have 4 links? Why? Number of instant centers is n into n minus 1 by 2, NC2. Okay. So, for a 4 bar you will have 6 instant centers. Okay. So, I have I12, I23. So, if you look at the pivots, they are automatically instant centers, because they are common to both the links, okay, and they are going to have the physically they are common points to both the links, the pivots, and they are also called permanent instant centers for that reason, because it is always that location in the two bodies, it is always going to be that location which is the instant center for those two bodies. So, this is I23, then I have I34 and I14. Okay. Now, we have to find couple more instant centers. The ones that are missing are for bodies that are not directly connected to one another, right. So, here the missing instant centers are I13 and I24. So, to do that we make use of the Kennedy-Arenhold theorem, which states that if you have three bodies moving in a plane, then the three instant centers will lie on the same line, right. So, and we use this what we call the circle diagram to help us find the instant center. So, here I know R 1 2 2 3 1 2 3 4 denote the 4 links. I know 3 4 and 1 4. Okay. Now, I want to find 1 3. Okay. So, if I look at this diagram, 1 3 is a common side to 1 2 and 2 3. Similarly, for 1 4 and 3 4. Okay. So, what that means is I13 lies on the line joining 1 2 2 3 and the line joining 1 4 3 4. So, this gives me I13. Okay. We have seen I13 before when we looked at centroids, right, fixed and. So, I13 is special because it belongs to body 1 as well, which means from the definition of the instant center, its velocity is always 0. So, in certain cases the velocity of the instant center will be 0. Okay, the velocity of this point I13 is 0 because it is common to both link 1 and link 3 and it has the same velocity in both the links. Now, let us look at I24. Okay, so, now I have I13, I have determined I13. The other one that I want is I24. So, from here I can see it is I12, I14, it lies on the line I12, I14. Okay, and I23, I34. So, it is this. Yeah. This will be I24. Is the velocity of I24 0? No, it only has the same velocity whether you consider it as a point on link 2. So, imagine that link 2 is extended to include I24. Okay. And you can also imagine that link 4 is extended to include I24. Okay. What this tells me is, what is the motion of link 2? The absolute motion of link 2 is pure rotation about I12. The absolute motion of link 4 is rotation about I14, fixed pivot. So, that means what would the velocity of this point be? I24, if I consider it, so from, because it is the instant center, velocity of I24 will be the same whether I consider it as a point on link 2 or link 4, right. What is the velocity of this point if I consider it as a point on link 2? Let us say this is omega 2. Velocity of I24 equals omega 2 into the distance I12, I24. Okay. And this is the same as omega 4 into I14, I24, because link 4 is rotating about I14. Therefore, I can directly get omega 4 as I12, I24 by I14, I24 into omega 2. So, I do not have to go through that. With the other method, I would have to calculate omega 3 and then. So, here in the 4 bar you do not see the use of it so much, but if you, when we look at the next, the 6 bar mechanism that we saw earlier, if you want to find omega 6 here, you can find that by finding the instant center that relates 2 and 6, I26. Okay. So, let us do that, let me do another example quickly. So, let us take okay, this is similar to the mechanism that we saw earlier, and let us say I want to find, okay, here is an interesting situation here. Suppose I give you omega 6 as my input, okay. I can't even solve this by the velocity difference method, okay. I am telling you I can't solve this by the method that I used earlier, because let me see 1, 2, 3, 4, 5 and 6, okay. So, A, B, C. If I look at this loop, okay, this particular loop, the coupler is not attached to any link that is part of the frame, link 5. So, if I try to find, say I know the velocity of point D, because that is my input, that is based on my input omega 6. Now, to move to the other links, I need to find another point on link 5 for which I know something about its motion, but in this case C is not part of a link for which I know the curvature of its path. In the previous case, C was part of a link which was pivoted to the ground. So, I knew the direction of its, I knew the curvature of its path, and hence I knew the direction of its velocity vector. In this case I do not know that. Okay. So, I cannot even solve this by the velocity difference method, by the relative velocity method. Okay. We will talk about another technique to solve this tomorrow, but now let us see if we can do it by instant centers. So, I want to find input is omega 6, output omega 2 equal to what? So, I have my circle diagram with now 6 marks on it, 3, 4, 5, 6, I12, I23, these are all the known instant centers, 34, I35, I56, I61, I14. So, all the known ones you mark on your circle diagram, 1, 2, 2, 3, 3, 4, 3, 5, 5, 6 and 6, 1 also 1, 4. These are all known. These are all permanent instant centers that I get from here, right. Now, if I want to find, this is what is missing. I need to relate, if I want to relate 2 and 6, I need to find I26. What is the path? So, if I want I26, it has to be a common base for 2 triangles. Okay. So, maybe I need I25 or I36. Okay. Let us see if, suppose I find I36, then I can find I26, right, because 1 2 1 6 2 3 3 6 will be. Now, to find 3 6, what do I know? What do I need? Here, if I look at this, if I find, so I know 3 5 5 6, if I find I13, then 1 3 1 6 3 5 5 6, that will give me I36. So, I have to find I13, the order in which I go is, I find I13, then I can find I36, then I can find I26. Do you see that? I13 is straightforward because this is just a 4 bar here. So, I have, this is I13. Okay. Now, okay, once I know I13, I16, okay, that is I13, I16 and then I35, I56, I35, I56. Okay. So, somewhere here is I36. So, now I have found I36. Once I know I36, I23, I36. So, I want to find I26 now. I23 and I36, I23, I36. and I12, I16. Okay, so let me just extend this. I12, so this gives me I26. So if I find I26, I directly get omega 2, because omega 2 into I12, I26 is equal to omega 6 into I16, I26, because I26 is a point that is common to both link 2 and link 6. Therefore, omega 2 is I16, I26 by I12, I26 omega 6. So, in some cases where it is not possible to solve by the velocity difference method, instant centers may work. But with instant centers, suppose the instant center is located out of the plane in which you are, when I say out of your working area on the plane, then you are in trouble. If you do not have a big enough sheet, then for a particular position you may not be able to do the velocity analysis. Again, it is okay if you want to just do it for specific. Graphical methods always are okay if you want to just do it for a few positions. Okay, if you want to do it for multiple, for the range of motion, you will have to go to an analytical method, and we will look at a couple more interesting methods. Okay.